Hello, I'm going to be a little bit faster. Sorry for taking some time to make the video. So on the previous lesson, we did arithmetic series and we did the proof because it's important. You now know how to prove the series and you know how to apply it, right? And we did two of the formulas, right, of the series, but I'll summarize everything at the end. So here we'll be doing the geometric series, right? So in your geometric series, just like we did in your geometric sequence, you understand that in your geometric series, you have, or your geometric sequence rather, you have a ratio instead of having a difference, right? And you understand that the only difference between the geometric series and the geometric sequence is that in geometric series, we are looking for the sum. We are simply adding, right? So now we want to prove the geometric series. But before we can even go there, I want to show you something quickly, right? So we can see that if this was the case and they gave you something like this, you'd see that you keep on multiplying by 2, right? So that would be your R would be 2. And remember that when we were doing the sequence, that AR to the power of n minus 1, that was your general rule, right? That was your general rule. So now we want to use this general rule to try and prove the geometric series, to find the formula for the geometric series, right? So if we find the formula for the geometric series, if we assume that we have the sum, right? This is the sum of the nth terms, right? We are no longer using Tn because Tn, that is your general formula, right? Here we are looking for the sum, right? For Tn, we are looking mostly for the terms. We are not really looking for specific term here. We are looking for the sum. So how do we go about? We know that A represents our first term, right? Remember we said that the only place where A doesn't represent your first term is in quadratic sequence, right? That is the only place. So this would be your first term, and then for you to get the second term, you'd have to multiply this A with R, right? And we saw that in the example I just gave you now. And for you to get the third term, you would have to multiply this with R. That will be AR squared, right? So you would do that until Jesus comes, right? And then we reverse this as we did on the other one, on the previous example, when we were proving what you call, when we were proving the arithmetic, right? So since this one is AR squared, for us, when we reverse this, we use ARN, right? Because remember that, you end here. If you ended at R to the power of 3, here, your next term when you reverse it will be N minus 2, right? But for us, because we ended at 2, this would have to be minus 1, right? So the reason why I'm ending at 2 is because already there's no need for you, because you will remember this formula, right? You will remember this formula. It will be easier to substitute this there, right? I hope I'm not confusing you at all. Right. So what do you do from there? You have to reverse. If I multiply this by r, you know that when you multiply by r, if I multiply this and this by r, this the bases are the same. It's r, and I have a exponent one day. So they have to add, and you see when I add this, they will cancel. So it means there it will be r to the power a, r to the power of n, right? It will be a r to the power of n. Right, so that will be your first sequence, right? That will be your first sequence, or your first equation, I mean to say, right? So that we will label that as equation 1. So for you to obtain equation 2, you have to multiply equation 1 by r, right? So you multiply everything by r. So this will be rsn, this will be ar, plus this one will be ar squared, this one will be ar cubed, right? So we keep on multiplying everything by r, right? And when we multiply, what's the most, okay? When we multiply, we are here. If we multiply this one by r, we know that it will be, no, I think I did made a mistake there. Okay, no, it's fine, guys. So if we multiply this one by r, we know that this will be ar to the power of n, right? And if we multiply this one by r, it will be A. Sorry for that, guys. Someone disturbed me. So, and I even realized that I made a mistake here. So, let me start afresh. So we're saying that it will be the sum will be A plus, for us to get the second term, it will be AR. For us to get the third one, it will be AR squared. So let's just leave it there, right? And then for us to get this one, it will be, I told you that you use this formula, right? So let's just take it from there. Let's leave ARN minus 2 and everything, right? Let's just take it from there and leave it there. So for you to get the second formula, you multiply the first one with R, right? So this is your equation 1, right? So you multiply the second one with R. So when you multiply this with R, you get AR. But instead of you writing AR here, you leave a space and you write it here, right? You will write it here. You leave a space here. So you multiply this one with R, the answer is this one. You multiply this one with R, it will be AR squared. So the AR squared, you write it here. And you multiply this with R, it will be AR cubed. It will be in between there, right? It's in between there. And we know that before ARN minus 1, there was ARN minus 2. So if you multiply ARN minus 2, the answer will be AR to the power of n minus 1. And you multiply this one with R, the answer will be A to the power of R, AR to the power of n, right? So that is how it is. Forgive me for the mistake, guys. So from there, this is equation 2. And then in equation, what you do, you subtract 1 minus 2, or you can say 2 minus 1. Let's say 2 minus 1. But I'll show you, even if you said 1 minus 2, I'll show you the difference, right? 1 minus, equation 2 minus equation 1. So this will be RSN minus SN. It's equal to 0 minus A, that will be minus A, right? This minus that will cancel. This minus that will cancel. This minus that will cancel. And then this one minus 0, it will be plus AR to the power of n, right? And from there, you take out the common factor, which is Sn, right? So it will be Sn, then in brackets, you will have R, you'll be left with R minus what is left here is 1, right? So that is equal to, take out the common factor here, which is A, and then what will be left here is negative 1 plus AR to the power of n, right? But we can write it in, this form, right? So it will be R to the power of n minus 1, right? It's that easy. So from here, what do we do? Because we want the sum, we have to divide by R minus 1, divide by R minus 1. So the final answer will be the sum of nth term is equal to A R to the power of n minus 1 in brackets all over R minus 1, right? So you use this one when your R is greater than 1. Right? If it happened that we said equation 1 minus 2 instead of 2 minus 1, what we would get is something like this, right? Let me try and raise it, show you exactly what we would get. So if we said 1 minus 2 instead of 2 minus 1, we would have Sn, it's equal to A 1 minus R to the power of n. Instead of having R to the power of n minus 1, then here we would have 1 minus R. So this one you use only if your R is less than 1. If your R is greater than 1, you use this one. So both of them are geometric sums, right? I hope that makes sense, guys. I hope that makes sense and I'm not confusing you. So that's the geometric, and remind me to give you exercises on that one because I feel like you understand. So I don't want to waste your time, right? I just want us to go and finish with this chapter. So we have something called sigma notation. So with your sigma notation, what we'll be doing is simply, it's still your series, but in your sigma notation, we are now representing this in form of a symbol, right? So instead of us writing the whole equation, we just simply represent it with this Greek E letter, which is for sum, right? So what you have underneath it, that is your first term, right? What you have underneath it is first term, always. And what you have on top of it is always your last term, right? It's always like that. And what you have on the side, that is your sum, or they give you the formula, right? Is the sum, or they give you the formula. It's that easy. This is how it is, right? And always the question that they will always ask you before you can even start, they will always ask you the number of terms, right? They will always ask you the number of terms, right? So how do you go about finding the number of terms? This is the formula, right? It is last term, I'll just write L, last term minus first term plus 1. This will give you the number of terms. It's last term minus first term plus 1, always plus 1, right? So that will give you the number of terms you have. Or other textbooks like say top minus bottom plus 1. It's one and the same thing, right? It is one and the same thing. And always when they give you something like this, they will say to you, evaluate, right? So people often get confused what they mean by evaluate. When they say evaluate, they're simply saying, give us the first 3 terms, and after finding the first 3 terms, give us the sum, right? The sum of what? The sum of the number of terms, because now you know how to calculate the number of terms. I hope that makes sense. Right, so let's take one example before we move on. Let's take one example before we move on. Let's assume they give you something um, like this, and they tell you that up there, or let's say they tell you here that you have x, and x is equal to 1, right? And they tell you that they don't know the number of terms, right? The last term is n, right? And then they give you that the formula is like this, right? It's x minus 1, and that is equal to 381, right? They gave you the sum, they gave you the formula. Already by looking at this formula, you can see that this is a geometry, because this represents a, this represents r, and this is n minus 1, right? I hope that makes sense and I'm not confusing you. So they say to you, the question is, they ask you to determine the value of n, right? The question is for you to determine the value of n. So how do we determine the value of n? I told you that always when you're given sigma notation, the first thing that you should always do is to find the first 3 terms, right? So how do you find the first 3 terms? You would substitute, right? So term 1, it's equal to, you will start with what you're given. You don't start with 1 always, because sometimes it will be 5 here. So you always start with what you're given. So when we substitute 1, it will be 1 minus 1, which is 0, and anything to the power of 0 is 1. So 3 multiplied by 1 is 3. So we understand that our first term will be 3, right? And our second term, but you have to write it down and substitute, right? So the second thing that we have to write, the next number we'll substitute with, because we go in chronological order, we'll have to put 2. So it will be 3 multiplied by 2 minus 1, that will be 1. 2 to the power of 1, that is 1, right? And 2 to the power of 1 is 2. So 2 multiplied by 3, that will give you 6. And what is the third term? The third term, it will be 3, we substitute 3 there. So 3 minus 1, that will be 2. 2 to the power of 2, that's 4. 4 multiplied by 3, that will give you 12. So now you have your first 3 terms, right? Which is 3, 6, and 12, right? So already we know that this is a geometric sequence. We know our A is 3. We saw it here, right? And we know that our R is 2. But sometimes it's important for you to guess that your R is 2. How did we find this R? We said it's term 3 divided by term 2. Remember the formula I told you on the first video, then we divide term 2 with term 1. Our term 3 is 12, so if we divide 12 with 6 and we divide term 2, which is 6, 6 with 3, you see that both of them will give you 2. So that is why our R is 2. right? And your A is 3 because that's the first term, right? And then now this is easy because now if you know that this is a geometric sequence, you know that you have to apply the geometric series, right? So we can simply say the sum of the geometric series is A, and we see that our R is greater than 1. So we will use which one of the two formulas? If you remember, we will use this one, right? We will use this one. So for writing this, you will get a mark because you understand which series to use, right? They won't tell you. We understand that our sum is 381 because they give us. So it will be 381 there. Our A is 3 because that's your first term. Our R is 2, so here it will be 2 to the power of n minus 1, and then all over 2 minus 1, right? And then from here, what you have to do is simply substitute because 2 to the power of 1, 2 minus 1, that will be 1, right? So if you cross multiply, you will still have 381 this side, right? We have 381, and then obviously this side you'll be having 3 in brackets 2 to the power of n minus 1, right? So what you will have to do from there on is to divide by 3 on both sides, right? So that you eliminate these 3. So you divide by 3, you divide by 3. So 381 divided by 3, that will give you something like 127, right? And then that side it will be 2 to the power of n minus 1, right? So we take this 1 to the other side, we give you 128, and then 2 to the power of n. And then from here, what you can simply do, you go to your calculator, type 128 equal to shift, and then there's a button which is written fact on top, right? And then that should give you something like 2 to the power of 7, right? And then 2 to the power of n. So the bases are the same because always when we have a variable that is an exponent that is unknown, you must make sure that the bases are the same so that you can cancel. Let me know if I'm too fast, guys. And then you cancel that and that, and then your n will be 7. So we sorted, answered the question, you're done. That is easy. Let me know if you want other questions, right? I will give you, or I myself will give you other questions, right? So you can see that this will continue forever, and this sum will increase if we continue adding terms. But we have what we call infinite geometric sequences, right? They are infinite. They are not going until infinity, just like that one, right? They are infinite, right? Whether you call it infinite or infinite, 6 and 9, right? So that one is infinite geometric sequence. So it means that an infinite infinity or an infinite geometric sequence has no end, right? It goes all over, right? Not all over, it goes on and on and on and on and on, right? So when it goes on and on and on, we say it converges, right? Sorry, man, we say that it diverges, right? So although an infinite geometric series never ends, it is possible to calculate the value for a certain infinite series, right? And we say the series is the converging type, right? And then we have the divergent type also. So what we are simply saying is that if it keeps on approaching 0, right, but it doesn't get to 0 exactly, we say that it is converging. But if it keeps on increasing, we say that it is diverging. If it approaches 0, we say it's diverging. It's converging. So an example is this this one. Right. So if you can go on and on, we'll see that this will never get to 0. Right. This will never get to 0, but it is approaching 0. Right. So that is it. The closer it gets to 0, we say that it converges. So when a series converges, it means that your ratio will be greater than -1, but it will be less than 1. If it converges, this is the rule, right? So this is what we are interested in, because what's nice about maths is they'll never ask you what is converging and what is diverging. You just have to understand how to calculate. So if they tell you that the series is converging, already in your mind you should have this formula in mind. You should know that when r is greater than -1 but is less than 1, that series is converging, right? Or if they give you a series and then they ask you if it's converging or diverging, for you to conclude, you must use this, right? So we have what we call sum to infinity, right? So if we want to calculate this sum of terms to infinity, we will use a separate formula, which says sum to infinity is equal to a all over 1 minus r. This is the formula for sum to infinity. And you understand that that sum infinity only comes if the series is converging. We understand that that r must be less than 1, but it must be greater than -1. Right? It's that easy. It's that easy. It's easy, guys. So don't stress yourself. With this one, I won't do examples because it's just substituting. Right? It's just substitution. Just give you one thing and we just do that, right? So let's now take a tricky question that they can ask you. They ask you to show that 0.9 or let's say 0.9, then you know that this dot means it's repeating, right? It's repeating. They ask you to show that 0.9, which is recurring, is equal to 1, right? So how do you show this? Then you can use a infinite series, right? So we know that if this dot means that this is repeating, we know that we can say this is the same as 0. This 0.9, if we take it to this two fractions, it will be 9 over 10, right? Because we have one digit after the decimal place. And then we have to add that with 9 over 100, add that with 9 over 1,000 until Jesus comes. Why are we doing this? Because we understand that this one is 0.9. This one is 0.09. The next one is 0.009. And if we add this, you see that it will give you 0.999. So this dot, since it means that it's repeating, it means we have more nines. So that is why we are adding it like this, so that we make it a series, right? So that we can show that it is really equal to 1, right? So from there, we can see from our series that our A is equal to 9 over 10. And we can see that our R, it will be 1 over 10, right? How did we find our R? We can divide 10(2) with 10(1), and that should give you 10(3) divided by 10(2). Because if you divide this with this, you can see from us to get from there, we kept on multiplying this with 10, right? So it means our ratio is 1 over 10. But if you don't understand, let me know. I will make another video, right? So sum to infinity will be equal to a over 1 minus r, right? You get them up for that. Your first term, that's 1 over 10, all over 1 minus 1 over 10. And then if you type this in your calculator and you do everything, you get that the answer is 1. So we've shown that this is equal to 1. By knowing what is a infinite series, right? So what they'll do, they just put sometimes this in a word form. They apply them in real life, right? We call them real life applications, right? So nothing changes there. You just have to follow the statement that they are giving you, right? And we will also do this when we do financial maths also, right? But I will try to give you, if you understand, ask me to give you a video, not a video, an example of one, right? Because I want us to also apply it in percentages, right? It's that easy. But we only do that if you understand, right? And sometimes they'll also give you in terms of patterns. So that concludes chapter 1. If you understand, the next chapter will be functions, and we will continue with I'll try to do the video for the first chapter of life science and first chapter of physics before sleeping today, so that we're progressing. So that concludes chapter 1, and hopefully by Monday we should be done with chapter 2, and we'll move on, because chapter 2 will be doing your functions, which that's my favorite chapter. We'll be doing functions, inverses, and the logs. So that's it from me, guys. The video is very short. If you are done and understand, let me know so that I give you examples. You do them. If you understand and you're correct, we move on.